So welcome to the Yale Engineering Invited Speaker Series. We have another exciting presentation. So this is a featured event, was launched last year, and I am here in my role of a Deputy Dean for Research. I'm here to welcome Dr. Mukesh Khare from IBM. There will be about 30 minutes with introductory remarks from Mukesh for the first half an hour or so. Then we will open it with questions for the audience. And at the conclusion of the talk, there will be refreshments and informal gathering that everybody is invited to. Before we begin, I would like to first of all thank the Tsai City for welcoming us to this wonderful space, and we are very grateful for that. I would also like to introduce Mukesh to you and his accomplishments and the path, his path over here. So he's a Yale graduate in 1999. He was a TP Maz student in electrical engineering. He's currently General Manager of IBM Semiconductors and Vice President of Hybrid Cloud Research at IBM Research. And in his role, he leads a team of more than 1,500 people. He's situated in Albany, but spends his time between Yorktown Heights and Albany. Mukesh and his team, they are working on redefining the computing for the future, for the age of artificial intelligence and quantum. And it's changing rapidly. He's been involved in semiconductor process technology, in chip design, and in system architectures. Also introducing, over his career, he went from 119 nanometer technology down to 7 and then 2 at IBM. And he is currently working on high-performance computing and hybrid cloud and ecosystem development for advanced semiconductors. So I look forward to learning more, and now let's welcome Mukesh Khare.
Well, thank you. Thanks for introduction, and it's just wonderful to be back here. I used to work in this building, Beckton Center, 3rd floor, TPMA lab, and they are just great memories I have of my little bit more than 4 years at Yale. Just to share with you myself, this is me in TPMA's lab doing gate dielectric characterization, and I'm this is TPMA, room number 319, 3rd floor. I would spend a lot of time in 3rd floor alcove with TPMA and all his students. And this is my lovely wife, Yamini. We got married towards end of my PhD, and we have the best memory that we can have of New Haven and Yale. So I'm just so happy to be back here and share my journey with all of you. In particular, I was very well connected, very deeply connected with Professor TP Ma. TP was just an amazing mentor, coach, advisor, the best person you can ever meet in your life. Everything I am, honestly, is because of Professor TP Ma, who made such a big impact to my life, my journey, and I can't be more grateful for being, joined TP's lab. It was all by chance. I had hoped. I used to read a book from Professor TP Ma when I was in India at IIT Bombay. It was a book written by TP Ma called Radiation Effects on Gate Dielectric. And I would look at, who is the author? And author is TP Ma. So we wrote to TP Ma, and TP Ma said, you can come work in my lab. I was like, okay, wow. And that was dream come true. And there I am, 30 years later. Meeting TP Ma. I became distinguished engineer at IBM in 2012, and I was so happy to actually dedicate my distinguished engineer certification to TP Ma for his 70th birthday. We were very happy to come here in 2015 when he was 70-year-old to celebrate his, I'll say, legacy. And TPMA has produced just amazing students. I'm sure the most famous of TPMA students is the CEO of TSMC. C.C. Wei is a TPMA student, and many, many more. He's the most famous one that we all know about. It was very sad that during COVID time that TPMA passed away, and that was just heartbreaking for all of us, for all our family, and we joined to celebrate TP's life. So thank you, TP, for giving me everything that he could, as I said, and making me who I am. TP also got me to a journey. TP got me to a journey where he brought me to my next phase also to IBM. And TPMA had a very strong relationship with IBM. He actually worked at IBM, then came back to, he graduated from Yale, then joined IBM, and then worked at IBM for a few years, and then came back to Yale as a professor. And but he had a great relationship with IBM, and many of TP students will end up at IBM. My manager was from Yale. I'm from Yale. Many of my executive team members are from Yale. So I'm very proud that TP continued to send best students to IBM. And here I am, 25 years later, working at IBM, and we're just proud that I will say it's just impossible to think about computing without thinking of IBM. IBM is the only company in the world which is more than 100-year-old, still working in the field of computing. Most computing companies exist for few decades, but IBM has been continuously reinventing itself for more than 100 years now. We have about 250,000 employees working in 180 countries all over the world. But we have evolved our business. And these days, you may not see IBM as much in your day-to-day life because we only work with enterprise and government. We don't have a consumer business anymore. Obviously, at one point of time, we used to make cheese cutters and scales for measuring meat. That's where the company started, and here we are. We are still making some kind of a computing device, but it's very high-end, only for as I said, only for bank, airlines, government. Those are our clients, and we kept moving in the value chain. Because we are a U.S. company, we have to be like very, very high-end when we produce our outcome. Along the way, IBM. At the heart of IBM is IBM Research, which is the innovation engine which drives what comes out of IBM and as a company. And IBM Research is also very academic, and that's why I'm very excited that we continue to stay connected with university and many awards along the way for our breakthrough research in many, many areas, broadly in the field of computing. So as it was mentioned, this is a very exciting time in the world of computing. It has not happened for generations that the three branches of computing or three areas of computing, which is the traditional computing, that is the high performance computing, artificial intelligence or AI computing, and quantum computing. All of these three branches are coming together. This is after a long time, such an amazing convergence is taking place, and we are fortunate to be living in that era where we can have an impact on how these three branches of computing will come together and can really benefit all of us, benefit society. And then that's what we call what's next in computing, which is essentially convergence of these three branches of computing. And then how does computing gets consumed? That is also changing. Computing is getting consumed through cloud or through hybrid cloud, what we call, which is both cloud as well as on-prem, seamlessly across both of those environments. So today I will focus a little bit more about one area of computing that is very exciting, which is the AI computing. And I'll leave quantum computing for next time when I get to talk to all of you again. So clearly, today's talk is all about AI or Gen AI workload, which is driving a huge excitement and huge market opportunity for the whole world. There is an expectation that the world GDP will grow by about 7% due to Gen AI or due to artificial intelligence technology. This is a very, very transformational technology. For our generation, it could have trillions of dollars of impact to the world economy. And that's great for us. It's great for us that we are part of creating that technology. It's great for that all of you are part of generation who is going to define this Gen AI for the future. And that also drives a significant growth in semiconductor industry. Because at the heart of all of the computing is semiconductor technology. Whether it's high-performance computing, AI, or quantum, they all depend on semiconductor technology. So semiconductor industry is also evolving, changing, and expected to become a $1 trillion market by end of this decade. So clearly, it's the workload that drives the industry, and it's the Gen AI workload that is driving the semiconductor industry for today. So share with you a little bit more about, how we see this industry, evolving. Okay. All right, so just to give a little bit more context about Gen AI, the demand for compute approximately was doubling every 20 months. That's approximately the Moore's law. But because of this Gen AI computing now, the demand for compute is doubling every 6 months. That is I'll say very, the demand is actually growing even faster than every 6 months now, considering what's the rate at which these models are getting created and getting deployed. So again, it creates opportunity for all of us to innovate and being able to satisfy this ever-increasing demand. Now that said, there is a challenge with that. Essentially, we are consuming a lot of power, or we are almost burning up the planet by just creating these very, very large and very complex models. To give you an example, how much energy it takes to create these models, this size of the circle is about 1,000 megawatt hour that can essentially power a US house for 100 years. And look at the size of energy that is consumed just by creating one GPT-4 model. There is 51,000 megawatt hour of energy to generate that model. That means clearly something has to change because obviously this is not a sustainable way of creating this AI technology. Yes, Gen AI technology is important. It's transformative technology. However, this technology has to move in a much more sustainable manner so that it can really be it can grow as well as grow in a sustainable manner and coexist with everything else that's going on. So that's an area which is again an area ripe for innovation, not on the model side, but also on the infrastructure side, like how do you build this model, how big the model need to be, and what type of problems that it can address. And how do you address that problem? So this is where the three parts of our society comes together to essentially create technology for the future. The way we look at it is the industry, the academia, like all of you at Yale, and government comes together. They have to come together to be able to solve these I'll say, huge problem or huge opportunity for our society in the space of Gen AI. And we are finding it. I spend most of the day today with many of your colleagues, some of your professors, to understand many of the exciting work and I'll say groundbreaking work going on at Yale. And I'm very proud to see that Yale is continuing to make progress in the frontier of science here. Now I will go a little bit more into specifics of technology. And as you can see, there is always a workload that drives technology forward. There was an era of personal computer which drove technology to, or miniaturization to, let's say, 1 billion transistor on a chip. And then came the era of mobile phone, data center, which drove further miniaturization, and more innovations came along the way. And here you can, most advanced chips these days are built using almost, let's say, 50 to 100 billion transistors on a single chip. However, this new era that I was describing earlier on, era of deep learning, GPT, is going to take us to putting more than 1 trillion transistor on a chip. That's just an incredible, accomplishment. I would say incredible accomplishment for humankind for being able to do that. It's mind-boggling. Sometimes, we work in that society and we cannot even imagine how do you put 1 trillion transistors. All of them are working on one single chip with such a high yield, and still, this technology is, as I say, sometimes more complex than rocket science. Rocket science is not even close to the type of work that we are doing, all of you are doing in this world. One way to do this is one of the area that we have worked on at IBM quite a bit is to build partnership. Because we are good in certain areas, but we are not good in everything that we do. And that's why we create this ecosystem of partners. We have a very large partnership ecosystem very close to where we are right now at Albany Nanotech facility. It's a public-private partnership where we work with New York State and many, many entities in this broader semiconductor ecosystem, essentially collaborating and co-creating and driving technology forward. Because that's the way, every partner, every company brings unique value to the table, and then we can then make things better by learning from each other. And at the end, every one of them get value out of it as well. So this is this also is a leveraged investment. This site has already invested more than $15 billion in capital to be able to get to where we are, and we are continuing to make progress beyond that. To share with you some of the more recent progress, just last year, as I was describing, on the government side, there was a lot of investment from US CHIPS Act towards driving innovation in the area that we are all interested in. In December of 2023, $10 billion investment was committed towards advanced lithography technology. We call that high NA EUV center. And then just last year, CHIPS Act selected this facility for as the National Center for EUV R&D. And we are very proud of that type of investment, because that's the level of investment that is needed to continue to make progress in this era of again, Gen AI driving semiconductors. And at the heart of it, one of the company that is driving this is the EUV technology is ASML. And ASML is right in your backyard in Connecticut, in Wilton, Connecticut. ASML, in fact, have the biggest manufacturing facility and R&D facility outside of Netherlands is in Connecticut. So we are very proud that in this neighborhood, the most consequential technology for the world actually is getting created right here in Connecticut. And we in Albany, which is again very close to where Wilton is, are in the same ecosystem to be able to drive this forward and together. So looking at all of that thing, what is our roadmap for semiconductor technology? So I had, as I had mentioned earlier on, I had an opportunity when I joined IBM in 1999. We worked on 180 nanometer technology. And since then, I got an opportunity to work on many aspects of technology. And in 2015, we created world's first 7 nanometer chip technology using EUV lithography. And since then, we announced the next device structure called nanosheet device structure. This is a version of gate-all-around device structure. And in May of 2021, we announced world's first 2-nanometer chip technology. And we are working on perfecting that technology with a partner and helping that to be ramped up in high-volume manufacturing. But obviously, it doesn't stop, and we are continuing to make progress. And we are looking at all of you to be part of this journey. And as you can see, this roadmap continues. And now we are working on what is there for next 10 years. And we are introducing a new device structure. We call that device structure nano stack device structure. And you will hear a lot more about this innovation that will continue the semiconductor technology journey at least till end of 2040. So there is a lot of opportunity for all of you to participate and create this future together. Many people ask me, is the semiconductor innovation over? Is the Moore's law over? My answer is no. It will be over only when our creativity gets over, or when ingenuity and our desire to do better and bigger things gets over. We are on a very strong and positive trajectory, and I do believe that this technology will continue to drive industry forward for at least another 10 to 15 years. And then I'm sure you will all come up with some better idea beyond that as well. Now, so that was more around compute side of the equation. Compute is important, but as we know, if you can compute, you always have to communicate. And these models that we are building these days require a lot of communication. And what we have found is that the rate of compute or improvement in compute have been making good progress. Despite a lot of challenges, it's making progress. However, communication is not making as much progress. For instance, interconnect bandwidth has not moved as fast as the compute has moved in terms of improving speed or efficiency or et cetera. There's a huge gap between improvement in compute versus communication. So this is an area that we are very passionate about because to build these large AI model, you need a very distributed system. You need thousands and thousands of chips. They are working together, accessing each other's state, each other's data. They have to access memory from various different places. So we need to be able to figure out how do we address that bottleneck of communication. And the best way to address communication is to move from electrical to optical. We already know the answer. The bandwidth for optical is very high. It's always in the range of terabits. However, we are still not able to overcome the last mile, like in the communication, the broader communication world. The whole communication is now in optical world. But if you look at the chip, when it comes to chip, it's still electrical. So how do you connect optical fiber directly on the chip itself? And that's the challenge that we were working on. And we are very proud that towards last year, December of last year, we announced a very innovative technology called co-packaged optics technology, where essentially what we're using is a polymer optical waveguide that can essentially provide you a fan-in of optical fiber, which can be connected on the one side of the optical waveguide, and that zooms into a very dense lines and space that can then be coupled with the chip itself. And that provides as much as 6 times more optical fibers at the edge of the chip itself, at the edge of silicon chip. That can increase our bandwidth by 80 times, and we can reach as much as more than 10 terabits per second per millimeter bandwidth. That is the type of bandwidth that we need, and that can really give us the type of communication that you need to be able to serve the need of these compute plus bandwidth for the Gen AI workload. So that was about technology. I will talk a little bit about the workflow itself. When you're building these large models, and deploying these large model. It's not just about model, it's about the entire pipeline of where you start and where you end. So first you have to start, when you're building this large model, you have to start with data preparation. We need to be able to make sure that the data is good for us to be able to use that in a model. So we use AI capability to filter the data itself and make sure that data does not have hate, abuse, duplication, profanity. All of those things need to get cleaned up before you can use that data to build the model itself. And then you work in a distributed training environment so that you can distribute this workload across, in this case, thousands and thousands of GPUs to be able to build this very, very large model. And then you need to be able to validate this model as well. That means you need a very, very strong distributed infrastructure and validation capability. And then beyond that, that's your general, or that's the foundation model. Then you have to, then what you're doing is you're adopting that model for certain domain. What is this model used for? And you can use some domain-specific data. There's a lot of data that is not out there in public. So a company or a user can use their private data to fine-tune that model or for their specific application. That will increase your accuracy quite substantially from where this general foundation model will start from. So then you work towards model adaptation or model tuning. And once you're done with this, then you infer, or you basically deploy this model for inference. And then this cycle continues because there's always new data getting generated. There's always new data that you want to use to be able to improve these models. So you need to look at, when you're building your infrastructure, you're looking at the entire end-to-end workflow for building these large models. So one area that is getting a lot of attention and where we are very focused on is the AI accelerator or the AI chip itself. I was very pleased that earlier today when I spoke with many of students and faculty, I see a lot of research going on at Yale, especially in this domain, to being able to build more and more energy efficient accelerators. And we at IBM are also very much focused on building these energy efficient accelerators. We call them AIUs, or just like CPU, GPU, AIU, which is Artificial Intelligence Unit, which is completely focused on designing chip from scratch or just from the clean sheet of paper. How do you design the most efficient chip for the type of workload that you are interested in solving or addressing? So we are looking at it fundamentally from first principle, and we have designed 3 types of accelerators. They are in different level of maturity. One is very near term, which is called IBM Spire, which uses essentially low precision computing, all in digital domain, and it's already implemented in our 5 nanometer technology. And then the second architecture that we are working on is called the North Pole architecture, which is essentially much more brain-inspired architecture, where we are essentially putting a lot of memory on the chip itself. So the chip and compute and memory are both sitting on the same chip, and that really gives you significant improvement in compute efficiency. And then longer term, we are working on analog AI technology, where we are leveraging the power of analog computing. So one of the, essentially computing world started from analog computing, but then we went in the digital world because we did not have enough precision in the world of analog computing. However, as we are learning, the Gen AI workload is not looking for very high precision. We are not doing 32 floating point computation in the world of AI. You're trying to recognize somebody's face, which is very different computation than being able to do a very complex spreadsheet and calculate numbers. So we are able to learn from that, and we believe that we are getting on a path where we can live with low precision, still get very high accuracy. And that's where analog computing comes in. So that's a very exciting area for us that we are working on, and I saw that many of our colleagues at Yale are working on those areas as well. This is just a little bit more specifics around where do various different accelerators belong. either in the data center space or in the automotive and industrial space, the 3 accelerators that I talked about, which kind of covers a very broad spectrum of application or use cases. That said, in our world, it's a long journey. In the world, especially in the world of hardware, it takes a long time to go from where you have an idea to actually you can deploy that in a real production environment. For us, to deploy this low precision computing capability, we started in more than 5 years ago, and we have to keep validating it, keep getting results, and keep deploying it so that we get more and more confidence being able to then deploy it in high volume. We plan to deploy this digital accelerator this year in our high-end Z systems and power systems. A little bit about North Pole project. This is a project that we are very proud of. We had a project before that called True North project, which we drove for the first time in the world using spiking neural network architecture. It was driven through our lab in California, Almaden Research Center, where we were really able to design chip truly using how brain works. And then, however, the chip architecture was possible, but as you know, it's the software ecosystem that kills you in the world of AI. And we had to adapt and move in the direction of more traditional AI accelerator design. And however, we are same here. So we have adopted that in this project, North Pole project, which is now brain-inspired project, which uses essentially non-von Neumann architecture, where you're performing computation right next to memory. Both compute and memory both are sitting on the same chip, and it's really providing very, very high efficiency for the type of workload that we are interested in. More than 25 times improvement in compute efficiency by using this chip architecture. And we are using it now to build racks to be able to use it even for large models, and we are experimenting in that space as well. Finally, this area of analog computing is another area that is, as I mentioned earlier on, is very exciting for long-term research, and it's coming closer and closer. We have been able to put together this analog AI chip in 14 nanometer technology with 13 million PCM or phase change memory based synaptic element, and being able to demonstrate that we can run very complex model on this analog AI chip as well. And here we are. This is a technology where we are looking at it really at the long term or a frontier of how we can use materials research. And essentially now, it's a full stack effort where you are optimizing material, you are optimizing chip design, you are optimizing your models, and you are and you understand the model architecture so that you can connect the dot all the way from application to the material science, or how do you build this better synaptic element. And we are, in this particular case, we used a phase change memory material, which essentially enables you to, depending on the, you can adjust the resistance of this device, which essentially means that you can store different weights as the model is getting deployed here, and that's a very efficient way of performing compute, and you can use very simple properties like Ohm's law to be able to perform multiplication. Versus doing a multiplication in a traditional way is just very complex, going back and forth between memory and compute. And we have embedded that, as I mentioned, in the 14 nanometer technology, and starting to open source it so that many of you can also practice, learn how to program or how to translate a program into an analog AI chip. And we are trying to bring the community along with us as well, as we are pushing the frontiers of this technology. So with that, I will conclude by saying that it's the combination of industry, academia, and government coming together is what is needed to continue to drive what's next in both semiconductor and AI technology. Thank you very much.
Thank you, Mukesh, for an exciting presentation, an inspiring one. So the talk is open now to questions from the audience. I don't think this thing is on, but I can talk loudly enough. And the first question, without much ado.
No, thank you very much.
This is Yale University. Yeah. I think it's Yale branded.
I got Yale thing too.
Yes. I don't know if it's on.
Thank you very much for coming to talk to us. My name is Ray, second year MBA. I'm just going to go ahead and ask you about DeepSeek and the market crash. Because, how do you see that? Has there been research going on within IBM to verify what they're doing? Like, is the energy efficiency really real?
Oh yeah, that's great. DeepSeek, as you can see, this technology is moving really fast. I don't think we knew DeepSeek last week, and now everybody knows DeepSeek very well. So a couple of things. I will say, it's great to have DeepSeek come out there and talk about how much energy efficiency you can achieve, because as I was describing earlier on, these very large frontier model with a trillion parameters consuming, millions and millions of dollars and megawatts of energy and so much carbon footprint is a bad idea, in my opinion, right? This is not the way we want the technology to be created. So clearly, this has to get disrupted. And I think that's one area. That's a little bit of my opinion, but I really believe that we don't want to consume that much energy just to build these models. Okay, that's one. And by the way, these models have a lot of garbage. There's these models are big, but they're doing, you do not want the same model to be able to write the best poetry in the world at the same time being able to design a new molecule for a drug discovery. It just doesn't make sense. It's just so. But that's the way the world is going. Fine. But I think DeepSeek actually did a very good job where they looked at model architecture very carefully and designed it using. Also, they worked in the open source community, which is another very, very good thing. A lot of these big frontier models right now are closed. And that is really essentially creating a society where either you have it or you don't have it. Probably 5 companies have it and everybody else in the whole planet do not have it. That is also not an acceptable way. So from an IBM lens, we believe in open source. We really believe that we need to collaborate, and that's the reason software world has moved this fast. And it's very good to see that there is more companies who are generating very high quality model working in the open community. So that will really accelerate the camp, which is open camp, to be able to collaborate, to be able to see what's going on. In fact, we at IBM created an AI alliance, and Yale is part of the AI alliance, where we want to bring everybody else who wants to collaborate in the world of AI together so that we can create better AI technology. So good that DeepSeek came out, good that they showed results. Obviously, we don't know everything about it, but we understand the model architecture, and we are very actually happy to see those results. And these type of results will start to create this balance between closed world and an open world. I really believe that the open world is the right world. That's the world that can really generate the best outcome for society. And let it play out, and we'll see.
Hello, my name is Oscar, second year Master of Public Policy at the Jackson School of Global Affairs.
Okay.
I wanted to ask you on, we're seeing the technology and the evolution of technology, but we're also seeing that there are rare minerals and critical earth that are required to support it, and how the industry sees the possibility of finding sources of these materials outside of a few countries like China and Belgium, for example.
Okay, so this is another geopolitical question. I'm getting like two. Very good. I think these rare earth materials are definitely very important, and those materials actually exist everywhere, including US or every country. It just we haven't invested our resources to get them out and being able to get to the right purity level so we can use it, right? So this will actually encourage those industry to be able to go extract those material and being able to make them useful for semiconductor or other industry. So I will say that I think this is the part of business kind of, if you can get something cheaper somewhere else, then you don't spend time on. Well, if you're not getting it, you're going to spend time on. So it's not the materials don't exist in different countries. It's just we haven't invested time and energy. And I think if needed, then I'm sure industry will go invest and government will go and invest and make sure the sources of those rare earth materials are available in like-minded countries.
Thank you so much for coming back to Yale, and thank you for the amazing presentation. I guess my question is, I'm wondering what the role of government is, I guess on top of incentivizing innovation, can do in the regulatory landscape to sort of, I guess, like respond to these challenges of, I guess, like energy security, energy shortages, whether in, I guess, like allocating I guess like which sources energy can go to, or like building up the grid, to sort of, I guess like balancing that with like innovation and computation. And I'm wondering like what your sort of, I guess like opinion on that is.
That's great. Another very good policy question. Few things. I will say during COVID, government realized that all over the world, not just US, but the world realized that some of these technologies are very, very critical. Very critical for economic growth, for national security, for everything that we do. And we realized it because of the vulnerability of supply chain that we all saw. So many countries are investing and stepping up to incentivize these industries to be, revitalized. I'll look at it a little bit myopically from US lens. Semiconductor industry was created in US, right? I mean, the transistor was invented in Bell Labs, right? And DRAM was invented at IBM. So we created this industry. However, we kind of did not pay attention to it, and we did not invest in that, and let it kind of disappear. And yes, we love application. We love to build these models, but these models at the end run on a chip. Models do not run anywhere else. So clearly, government realized that they need to pay attention to these critical industry, and both administration is, at least in the US, is supportive of that. Many countries like Japan, Europe, India, many countries and all over the world, they are investing in this fundamental technology. I think this is my opinion, that there need to be guardrails to make sure that we are not going too far in one or another direction. However, too much prescription on where to use this power from, or exactly what to do with this technology in every aspect, it just slows down the innovation. It just so I think countries to find that balance, that over-regulation is just not good for innovation, but no regulation is like jungle. So how do you find the balance between those two? And different regions have different opinion on that, but we have to find a balance. I just think that over-regulation will just slow us down. And as you can see, in the US, pendulum swings all the way from one end to the other end. And I'm sure eventually we'll find a happy medium as this industry, evolves. So that's my kind of broad answer to your question.
Hello. What do you think is the future with generative AI or AI and biology or chemistry?
Oh, biology and chemistry. That's a great question. First, I will say that generative AI will accelerate the rate of innovation in the world of biology and chemistry, because you know there are many challenges that those industry face, and we human beings are not knowledgeable enough individually to be able to solve that. And the methodology, that's, in my opinion, is very iterative and very experimental, which is important. But if you can use Gen AI, and if you can use Gen AI to be able to accelerate your rate of progress, I think that is very valuable, whether it's finding a new drug for disease, or finding a better chemical so that you have less PFAS, as an example. So I will say that it will accelerate the rate of progress in both of those industry. I don't know. I'm not an expert in and I know there's research going on here where is a human chip interface, etc., which I can't comment. But we are working on really using generative AI to be able to detect PFAS, as an example, in your processes, to being able to identify and hopefully accelerate the building of new material that can have less impact or detrimental impact on planet. Those are the areas that we are working on, and I really think that Gen AI will help us move faster to find a solution to those challenges.
Hello?
Yes.
What's your opinion on brain-computer interfaces? What do you think, how soon do you think it will take off, and what effect do you think it will have on the semiconductor industry?
Well, so this is, first of all, there are more faculty and more students here who know much more about it than I know, so I just don't want to be speculative. And Elon Musk knows a lot more about it with his company. So I think that I can only say very generically that I think that area is an area that is going to continue to grow, and we have to see how, as I was describing to, I think, one of your faculty talking earlier on, that the world of Gen AI right now is generally in the digital world. These are all models. You're all getting results which you can look on a phone or on a computer, etc. We are not moving Gen AI truly into a physical world. And I think this the topic that you're bringing up, that will, understanding that space will help us move from a digital world to a physical world, and hopefully in a positive direction.
My name is Jonas Cotone. I'm a fifth-year PhD in applied mathematics. So you mentioned earlier about how in the analog computing regime, there's some benefits because you get this trade-off between you don't need as much precision, but you can get pretty high accuracy, particularly for like Gen AI applications. And I know this was largely focused on Gen AI, and it was very interesting, and I'd love to hear you going over like IBM's role in terms of building an infrastructure. But going off the question, not the last one, but the one before, we were talking about applications of AI in scientific purposes, and engineering as well. Scientific machine learning often is actually concerned a lot about, the precision of these results, particularly to sort of challenge and improve on previous computing like algorithms and other things, more traditional like numerical analysis in these sorts of fields. So I was wondering what kind of things is IBM doing that maybe are also working on maybe the side more and actually how to produce precise results using these large deep learning frameworks. And second of all, do you see a market for that in the near future? So, yeah.
I can imagine there is market for that. I think that, and also, although we are learning about the low precision computing and analog computing, at the same time, our clients are as I described, enterprise. So if I have a client who is a bank, and you can say your bank balance is approximately, this range, that's a problem, right? So we're trying to find that balance where we are applying We are applying, let's say, low precision computing in giving a probability that this transaction is going to be a legit or a fraud transaction. However, we are not using low precision computing in terms of really performing high precision computation itself. So it's a balance that we continue to find between, okay, where can we live with low precision, high accuracy, because the probability is fine. Whereas other hand, okay, if I'm performing you're trying to check what's your bank balance, then you don't want low precision in that. You want very high precision in that answer. So it's always a balance.
Thank you for your talk. Jonas kind of beat me to it. Thanks, Jonas. But I have another question about the precision of these analog computers, and that's maybe what's the resolution of these phase change materials compared to like a 64-bit float? Or maybe more generally, what is the comparative information capacity of a network built by an analog computer compared to that inside of a classical computer that uses 32-bit or 64-bit floats for each of its parameters?
Yeah, I think, so I will say we are operating in on one side you're operating in 16 or 32-bit floating point. On the other side, we are operating in 2-bit to 4-bit. So it's a very long range on the analog versus high precision computing.
So the analog is 16 and 32-bit resolution on those, on each of these resistors.
Yeah. And what we are trying to get as much as being able to store 100 weights, 100 different states that I can individually distinguish from each other when I'm storing that information on the one single synaptic element or different resistance of that PCM device. But then it's always, that is not going to be enough. So it's truly not an analog. There's digital around it as well to reduce some of the noise, some of the error, to be able to make it compatible. So it's a journey. I will say the range right now is very big, and it's a longer term project for us to be able to get to a reasonable accuracy. And I showed you I think the number of individual synaptic elements were not too many. It's only 16 meg basically, which is very small. If you look at the size of model these days, they are in 2 orders or 3 orders bigger. So we have to look at smaller models in this case and certain class of application which can be used for those type of analog AI chip, and that's why we are describing it more towards edge and very relatively smaller model that can be deployed right now. I like, Yale is always very engaging. I remember those talks. I used to be sitting here and listening and thinking about it. So wonderful.
Just a question about, you had a slide on the non-von Neumann architecture that I just wanted to ask a quick question about because, so I think you mentioned one of the challenges is like programmability of that. And I was just kind of trying to wrap my head around how that would work. So, because you said there's basically like no memory off chip right? That's and right. So is it the case that that's already like somewhat programmable, or how do you work with something like that?
It is programmable. Mm-hmm. It is quite a bit programmable, but not as general purpose. So programmability is challenging. However, we have already deployed many networks on that chip itself as well. What happens is if you put the memory on the chip itself to eliminate this movement of data from compute to memory, then there is a limit on how much memory you can put on the chip also. And that limits the size of model that you can then deploy in that particular application. Or if the model is big and then you have to use many chips to be able to split that model across many different chips to be able to load that entire model. So I think that's the trade-off that we are studying. I think for small model, for the domain that chip was designed, it's perfectly fine. It's let's say tens of millions of parameter. But if you start to get to 100 million and billion, then you have to use like, okay, 100 chips or 1,000 chips. That's just not practical anymore. So it's the balance between the two.
Thank you.
By the way, when I was here, this thing did not exist. And this was a very nice area. In fact, it was not even paved when I was here first time. There was a nice tree over there. I don't know if anybody remembers that. We used to really love running from Beckton Center to Dunham. And then there was a tunnel. I think the tunnel, I was told, still exists. And I still remember carrying nitrogen cylinders. I don't know if anybody carries that or not through the tunnel.
Yeah, it still exists because I always go through the tunnel.
There you go, right?
Yeah.
I remember those dragging those nitrogen cylinder in the tunnel, then taking up to fifth floor in Beckton Center.
Yeah.
Right.
So I'm a student in optics. So you mentioned that the co-package technology you are using to improve the energy efficiency and also increase the bandwidth. So because I'm a student working on optics, so I'm curious about what's the technical challenges you are facing to employ this technology, and also what's the bottleneck for the co-package technology that you think would be the ultimate limit of the bandwidth and also the energy efficiency? Thank you.
That's great. I'm glad that you're working in that area, and everybody's happy about compute part, but people forget that you have to talk as well. And so yes, this is going to be a very exciting area for really innovation and disruption. Big disruption is coming because of the bottleneck in the bandwidth right now. There are many challenges, though. I will say it's not like ready to go technology. So even when you can bring the fiber optic to the chip itself, the signal still has to be converted from optical to electrical because compute is still in electrical. Now you're doing compute, you have reduced all the hops from chip to board to the server to rack to switch. Everything is optics. So that has definitely helped you, but you still have to have very high performing optical to electrical conversion on the chip or near chip itself, right? So that's like one area that one needs to work on. Now with respect to co-packaged optics, I think it's a technology that needs bigger ecosystem to be developed around it, right? Who are going to build those switches, who are going to build those electrical to optical converters. That means also that you have to redesign your servers, you have to design your rack, you have to redesign your broader data center. So there's a lot of effort needed across the board. But that said, the improvement in bandwidth and improvement in energy efficiency is just so much that as industry is going in the direction of needing better communication across thousands of chips who are either building model or deploying model, I think we'll move in that direction. It's like telephone wires. Telephone wires used to be copper wire, right, across everywhere. Now there's no copper wire anymore, right, because of same reason. So the optics hasn't reached all the way to chip. So it's all about infrastructure and ecosystem. I don't think there is anything fundamental. There's no fundamental barrier that need to get taken over. It's going to be a lot of engineering and a lot of ecosystem building around it, basically.
So this concludes our questions and answers section. And I would like to thank you, Mukesh, for coming, sharing all the exciting developments at IBM and really cutting-edge stuff. And you're also helping with our goal of bringing the leaders in the engineering from industry to the campus and interact with us. And thank you very much. And I would like to thank everybody else for being engaging, asking questions, coming, and welcome. That's now we have refreshments, and until the next time.
Thank you. Thank you very much for joining.